Inductive proximity sensor contains three main components: coil and oscillator to produce a magnetic field, and a detector to monitor oscillation to produce an output. Inductive proximity sensor contains three main components: coil and oscillator to produce a magnetic field, and a detector to monitor oscillation to produce an output. The oscillator circuit generates a high-frequency electromagnetic field that radiates from the end of the sensor. When a metallic target is entering the field, this causes the oscillator amplitude to change, increases or decreases depending on the design. The oscillation or frequency you see on the screen is for demonstration to show that there is a change happening. Then, the detector recognizes the change in amplitude and produces an output accordingly. Once the metal object leaves the sensing area, the oscillator regenerates and the sensor returns to its normal state. Now, to go a little bit in depth, what happens is, once a metal object enters the magnetic field, an induction current or eddy current flows in the target caused by electromagnetic induction. So, eddy currents are induced on the surface of the object. The eddy currents on the object absorb some of the radiated energy from the sensor, resulting in a loss of energy and change in frequency. In any application, the sensor detects the changes in frequency and transfers the data to PLC input module. Depending on the proximity sensor type, the data are connected to analog or digital input module. And this is in general a demonstration of the operation of inductive proximity sensors under the electrical principle of inductance. That is, a fluctuating current induces an electromotive force in a target object. Usually, it is shown in the datasheet if this is an analog or digital inductive proximity sensor. This is an example of an analog sensor giving an output of 0 to 10 volts. And in the same document, it also shows a summary of the operating principle of inductive proximity sensor. Capacitive proximity sensors are non-contact sensors. They sense both metal and non-metal materials, such as paper, glass, and liquid. They detect an object through the change in the sensor's capacitance, and hence the name. Here are a couple of examples provided by different manufacturers. Industrial capacitive proximity sensors look pretty similar to inductive proximity sensors. Generally, all proximity sensors have similar shapes. Capacitive proximity sensors produce an electrostatic field. Inductive proximity sensors produce an electromagnetic field. So the difference between them is in the operation principle, inductance and capacitance, and in applications, metal and non-metal. Capacitive sensors are a very common option to use within food and beverage industry and chemical processes. In this example, capacitive sensor is used to detect milk inside a container. The sensor detects empty containers to divert them into a different path using robotic arm or sometimes using push rod. Another application for capacitive proximity sensors is counting or tracking non-metal units like wood and paper passing on a conveyor. They're also used for level detection of liquid or other materials like granular or grains. In general, capacitive sensor contains a high-frequency oscillator and a sensing surface formed by two metal electrodes or dielectric plates that produces an electrostatic field. This is similar to an actual capacitor. This document is showing the general configuration of a capacitor. Capacitive sensor also has a detector to detect any changes to produce an output accordingly. In general, the operation principle goes this way. When the target gets near the sensing area, it enters the electrostatic field of the sensor. Then, the capacitance changes in the oscillator circuit. As a result, the oscillator begins oscillating. When the capacitance reaches a specific level, the output state of the sensor changes. As the target moves away from the sensor is back to its original state. Here are a couple of references if you want to read more about the operation principle of capacitive proximity sensors. A question might come across: if capacitive proximity sensors can sense both metal and non-metals, how would the sensor differentiate between materials? Like if we wanted the sensor to detect only the liquid inside a plastic container. This happens by knowing the dielectric constant, because for capacitive sensors, the change in capacitance depends on the material being detected. The higher the dielectric number of a material, the more sensitive a capacitive sensor is to that target. This is a datasheet from Rockwell Automation for one of their capacitive proximity sensors. You can see here dielectric constants of some industrial materials. For example, a glass is 3.7 to 10. Polyethylene, which is plastic, is 2.3, and water is 80. So, if we have two materials, like the example you see here, a plastic container with a liquid inside, let's say water. Since the dielectric constant of water is larger than plastic, that would allow the sensor to see through the plastic container and detect the presence or absence of the liquid located inside. Liquid targets generally have a higher dielectric constant that makes capacitive sensors a very common option to use within food and beverage industry and chemical processes because of their extreme sensitivity to liquid targets. Glass and plastic have a low dielectric constant value that makes them one of the best options as common materials to be used for the containers when using capacitive proximity sensors. Here is a reference showing a chart with dielectric materials, and on the right side of the chart are some common materials used for containers that would allow the sensor to see through. So now, one of the considerations when using capacitive proximity sensors is to keep in mind that the sensor sensitivity to humidity, moisture conditions, and varying temperatures, so the overall conditions matter when designing the system. Temperature sensors are used for measuring temperature and converting data into currents or voltages to be transferred to PLC. They are considered analog devices that produce readings like millivolts or resistant values. Here are examples of industrial temperature sensors provided by Siemens, Omron, and Honeywell. The main two types of industrial temperature sensors are thermocouples and resistance temperature detectors, or RTDs. RTDs and thermocouples come in different shapes and models. You can see here a list of models by Omron. In general, both types, as you can see, have similar shapes. Thermocouples are usually a little bit thinner and have two wires, but they are different devices and work using different operation principles. Here are a few examples of using industrial temperature sensors in industrial processes. Thermocouple is one of the common devices for temperature measurement. It consists of two different types of metals joined together at one end. The other end produces millivolts according to the temperature measured. Then, millivolts are sent to an analog input module of a PLC. Thermocouples have a hot junction and a cold junction. The hot junction, or measuring junction, is the side where the temperature measurement is desired. The cold junction, or reference junction, is kept at a constant temperature to provide a reference point. The produced voltage in millivolts is proportional to the difference in temperature between the two junctions. For thermocouples, usually the two types of metals are housed inside a metallic tube, and it's called a thermocouple probe, looking like this. Industrial thermocouples come in different shapes, as you can see here. They can be simple cable or inside probe sensor devices, or as a thermowheels, where thermocouples are housed inside cylinder fittings to protect them. Thermocouples are known for covering a wide range of temperature that can go up to 2,200 degrees Celsius. They have a fast response times, making them sensitive to any temperature changes. They are generally low cost when compared to other temperature sensors, and they have high corrosion resistance, making them a good choice in most industrial applications. They are used in many industries, like food and pharmaceutical industries, chemical, oil, gas, and energy industries. Basically, any industrial process that requires a temperature reading along the way. Thermocouples are classified by types. Each type is used for different applications. The most common types are J, K, T, E, and N types. There are also types for high temperature calibrations, like type R, S, B, and C. Each type has a different temperature range, as you can see here. Also, each type has a color associated with it. The color usually indicates the color of the positive lead wire. K-type, for example, is yellow, meaning yellow wire is the positive side. The type is usually shown on the specification page. Here's an example of a thermocouple from Endress Hauser. It shows that this thermometer can come in two types, type K and type J, and it shows the temperature ranges for each one. Details also included in the datasheet, like this example from Omron, showing type K, J, and R for these temperature sensor models. The color coding depends on the different standards used within different regions. So for the same K type, it shows here that it has different color combination depending where it's being used or manufactured. This table shows a summary of the leads color codes, as well as the different metals for each lead of the thermocouples. For example, for the K type, or manufactured. This table shows for these temperature sensor models. The color coding depends on the different standards used within different regions. So for the same K-type, it shows here that it has different color combination depending where it's being used or manufactured. This table shows a summary of the leads color codes as well as the different metals for each lead of the thermocouples. For example, for the K-type, the positive side is nickel chromium and the negative side is nickel aluminum. K-type is one of the common thermocouples used in industry because of its wide temperature range, low cost, and it's a nickel-based, so it has a good corrosion resistance, making it a very good choice in most industrial applications. There are thermocouple reference tables for each type. The reference tables show the relationship between the temperature and the corresponding produced voltage. Let's take this example to explain more. For the K-type thermocouple, if the temperature on the measuring junction is 300 degrees Celsius, then according to the table, thermocouple is going to give an output of 12.2 millivolts. If the temperature on the measuring junction is, for example, 260 degrees Celsius, then the output voltage is 10.48 millivolts. This helps in calibrating the thermocouple, in knowing if the device is working properly or not, and also helps in PLC programming to know what value is expected. The same is for the other types. Each has its own reference table. Tables are provided both in Celsius and Fahrenheit. You can search for the reference table of any type you're currently working with. So now, choosing a thermocouple type depends on the temperature range needed, the accuracy, and the application it's used for. Resistance temperature detectors, or RTDs, change resistance with temperature. This is based on the positive temperature coefficient of metals. That means the electrical resistance of metals is directly proportional to temperature. The hotter they become, the larger or higher the value of their resistance. An RTD consists of a fine wire metal wrapped around non-conducting core, which is usually made of ceramic inside a protective case. Another type of RTD consists of thin film layer of metal, usually platinum, into a ceramic base. Here are examples showing the different RTDs by Omega. RTDs are sometimes called PT100 sensors. PT meaning that the RTD wire is made from platinum. 100 means that at 0 degrees Celsius, the sensor has a resistance of 100 ohm. So the sensor name indicates its resistance at 0 degrees Celsius. This datasheet from Omron shows PT100 besides the sensor models, meaning they are RTDs. RTD wire can also be made of other materials like nickel or copper. Platinum is the most popular material for RTDs because it has a wide temperature range from -200 to 850 degrees Celsius, and it has a linear and stable change in resistance versus temperature relationship that gives a precise and repeatable readings. And this makes RTDs among the most precise temperature sensors available when compared to thermocouples or any industrial temperature sensors, even though RTDs have a lower range for temperature measurements. There are different types of RTDs for each application, so choosing RTDs versus thermocouples depends on your application requirements. Here are a couple of examples of different RTDs in the market. The operation principle of RTDs